Hello, everybody. So can we start now? Yes. So, okay. So the second part, we need to talk about this convolutional neural network, or ConvNet. So ConvNet, the goal of that part is to learn a higher order feature in the data using convolutions. So in this case, we need to work with data because in shallow learning, for example, we need to work with features, we need to extract features, we need to find the best set of features, for example. But in case of deep learning or convolutional neural network, we don't need to do this. We just need to work with raw data. So we need to know how those ConvNets try to extract those features from the raw data. So the convolutional layer is responsible for the systematic applications of one or more filters to an input. It will apply a number of filters to the input image, and it will try to extract some features using those filters. So the architecture consists of three types of layers. Any deep learning model consists of some input layers, and those input layers, it accepts only the 3D input, such as RGB image. It will just accept the inputs, and it will deliver it to the next layer. And we have one part, which is the most important part, which is called the feature extraction layer. This feature extraction layer, this is the convolutional part, and it's a repeated sequence of convolutional and the pooling layers to extract those higher dimensional feature maps from the raw input. And at the end, we will have classification layer. It could be classification layer or maybe some layers. It will be we call it fully connected layers, and those fully connected layers, we can call it the classification layers or the part which will make decisions. So at the end here, this is the model, how it look like. Okay. So we have this input image, which is a raw data, and we will send this one to a number of layers. Those convolutional part or feature extraction part, it will consist of a repeated sequence of convolutional layers, and each layer, it could be followed by a pooling layer, for example, right? So we have this ConvNet one. First convolutional layer, for example, it will extract some feature maps from this input image, and it will be followed by some pooling layers. The idea from having those pooling layers is try to avoid overfitting, for example. And it will be followed by some convolutional layers, for example, some pooling layers. So this is the conv part, feature extraction part. And at the end, we will have this fully connected layers or classification layers. So those fully connected layers, it could be 2 layers, 3 layers, for example. We call it fully connected layers, and that part will be in charge of classification. It will do this classification for us. So in transfer learning, for example, we can import a model which has been trained using some specific data sets. And the most important part for us is the feature extraction part. We will import the feature extraction part, and we will modify the classification part according to our problem. So for example, maybe someone is using this part for an NLP application, for example, for sentiment analysis. So in this case, the classification layer, the output layer will classify each input into one of those two classes, positive and negative, for example. Maybe someone else want to use it for some other application where we have more topics, for example. So in this case, we need to change the classification part according to our problem. So we will import this feature extraction part from another application, and we will try to add different classification part according to our new problem. So we can try to use the feature extraction part, which is a time-consuming part, because that part is very difficult to train. It requires a huge data set, for example, and it requires also time. So we will try to import that part from any other area, another application, and we will try to use it in our own application by changing this classification part. Okay, so maybe I need to clean. Again, it's okay. So the deep learning, how it works, we have an image. This is transfer learning. In fact, it's about VGG16, for example. So if you want to just very short about, just quickly about this transfer learning, for example. So in transfer learning, we have a model which has been trained for some images, for example. So we have this convolutional part here. It will try to extract some feature maps. I don't know what is going on. So we will have that part. This is the convolutional layers or the feature extraction part. We have this classification part, right? So this classification part, it consists of some dense layers, and maybe the last layer, it will be softmax layer. This one will be softmax layer because we need to calculate probabilities. So we can call it softmax layer, for example. And then the other dense layers, we can use some other activation function like ReLU, for example. So we can use here ReLU, we can use here ReLU, but this one we can use here softmax. So for calculating the probability. So anyway, the model at the end, it consists of two parts. One part, which is the feature extraction part, and one part which is called the classification part. And usually in transfer learning, we try to import this feature extraction and apply it to similar images. Maybe this VGG16, it has been trained using specific data sets, and we need to use it in some our application where we are using some other application, other images, for example. So we will import this feature extraction part, and we will modify this soft max part or the classification part according to our problem, for example. So maybe here we have, it has been used in binary classification problem. Maybe here we will use it in different application, for example. So we need to import the feature extraction part, and we need to design our own classification part according to our new problem, for example. But of course, it should be trained. For example, if we need to import a VGG16 from one application to another application, we should apply it to a data set which is quite similar, not very different from the other one. If we need to really extract the same feature maps or a meaningful feature maps. Again, we need to clean. I don't know. Sometimes it's okay. So, what are the building blocks of those convolutional neural network? We have three types of layers in CNN. We have those convolutional layers, we have pooling layers, and we have fully connected layers, right? So, we agreed that there are three types of layers. We will use convolutional layers and pooling layers, and each convolutional layer, it should be followed by a pooling layer, or maybe two convolutional layers followed by a pooling layer. And at the end, we will have this fully connected layers. Those fully connected layers, it's the classification layer. This one will be the classification part. And this block, convolutional layers and the pooling layers, they are stacked together, and we call it feature extraction part. So in transfer learning, we will just import this feature extraction part from one application to another application, but we need to remember to change the fully connected layers because we need to build these fully connected layers according to our applications. The convolutional layers are composed of some filters and some feature maps. We use filters. We apply those convolutional filters into our own images, the input images, for example, and try to extract some feature maps. Those filters are essentially the neurons of the layers. So, for example, we will see it. You can say that it's the neurons of this layer. It consists of weights, right? So each filter will be represented by one neuron. Each filter will be represented by neuron. So, for example, if you said that this feature, this convolutional layers will apply 5 filters of different sizes, or of one specific size, for example. So in this case, you can imagine that this layer consists of number of neurons, 5 neurons, for example. So we will have one neuron for each filter. They have both weighted inputs, and they generate an output like a neuron. The input size is a fixed square called batch. Each filter has a size, and it has an input, or it's a fixed square called a batch or receptive field. So each filter, in fact, has a receptive field. If the convolutional layer is an input layer, then the input batch will be a pixel values, because usually when the input is when this convolutional layer is an input layer, so we will apply those filters to the input image, right? So the input batch will be pixel values because we will apply it into pixel values. If they deeper in the network architecture, then the convolutional layer will take the input from a feature map from the previous layer. So we just it's only the input. Only the input convolutional layer, it will be applied to the raw data, and after that we will have some feature maps. So the filters of the input layer will be applied to pixel values, but the filters of the next layers will be applied to feature maps. It will be also, pixels of the feature maps, but not of the input image. Okay, each time it's, I don't know. Okay. So the feature maps, the feature map is the output of one filter applied to the previous layer. What is the feature map? Feature map, it is the output of applying one filter to the input from the previous layer, for example. So when we have number of filters, when we apply this filter to an input image, for example, or a feature map, it will generate a new feature map. A given filter is drawn across the entire previous layer, moved 1 pixel at each time, for example, because we have this filter and each filter has a receptive field, and we will move this filter across the image from right to left and from top to bottom. Each position results in an activation. When we apply this filter map on a receptive field of the input image, we will have one activation. We will have one activation of the neuron, and the output to be collected into the feature map, the output feature map. If the receptive field is moved 1 pixel from activation to activation, then the field will overlap with the previous activation by the field width -1. It's very important to have this kind of overlap. So we are not moving this filter each time by the filter size, because if we will move it by the filter size in this case, so imagine that the filter is 3 by 3, for example. If we will move it each time by 3 pixels, in this case, we will not have any overlap between those activations. But it's very highly recommended to have a kind of overlaps between each activation. So the distance that the filter is moved across the input from the previous layer, each activation is preferred. It's referred to as a stride. We have this stride. So the stride, it's the size of, or the number of, it's the distance at which the filter will be moved across the input. Because each time we will have one activation and we will move this filter by a distance. This distance we call it a stride, and we will represent this stride by number of pixels. So stride equal 1, which means we will move this filter by 1 pixel. If is a stride equal 2, it means we will move it by 2 pixels. We have something called zero padding, which is used to invent the smoke inputs with 0 values for the receptive field. Not to read off the edge of the input feature map. So we have something, we have this kind of overlaps, for example. So if imagine that we have this filter applied to the input image. So we will have one activation, and after that we will move it by the stride by 1 pixel value, for example. We will do another activations and so on. So the problem here, we will have so much overlaps in the input part, but not in the edges of the image. We will do this activation maybe only 1 time for those corner side, for the edges of the input image, but we will not have such kind of overlaps. So to avoid this problem, we try to use this zero padding to give more importance to the informations which are located at the edges of the images. So we will see it by examples. So we have this an input image here, and we have this kernel or the filter. This is the filter. Okay. This is the kernel, which we need to apply to. This is the input image, right? This is the input image, as you can see it here. We didn't use it. We didn't use padding. If we will apply this one without padding, we will apply this one to that part, right? And we will do one activation. And when we apply it here, we will calculate the output, and we will apply it to this pixel value, for example, right? And after that, we will move this kernel by 1 pixel or by the stride. So we will move it to that part here. and we will do another activation, correct? And we will go to the next line, next row, and we will go down here. It will be like this one, and we will do more activations and so on. So in this case, we can cover this image by four activations. So this, I mean, without zero padding, I can calculate those numbers by just four activations if we will not use zero padding. So zero padding, when we apply this convolutional layers, we lose some pixel around the perimeter of the input image. We will lose some information here, right? It can end up for successive convolutional layers. One solution is to add pixels of zero values around the boundary of our image. So the idea here, if we will do this, I will do here one activation. So this image, this pixel value at the corner, I will make it by yellow. This one, right? Lucy, we will scan this one only one time, as you can see, because I did one activations and I moved by one pixel. I moved here in that section. I will do another activation, so we will have this overlap in that section. This one will be scanned twice, and after that, this pixel value, which has two value, it will be also scanned only one time. I will make it by by yellow. So this one also, it will be scanned only one time, and we will go to the second line. We will do one activation. We will move to the right by one pixel. So at the end, those pixel values will be scanned only one time. Do you see? So those pixel values at the corner in blue, it will be scanned only one time, right? But other pixel values has been scanned twice, which means that maybe in this case, we will try to tell the machine learning model that the pixel values, which are the perimeter also, in fact, it's not only this at the corner, but also this one has been scanned twice. This, I mean, all pixel values has been scanned twice, in fact, except those yellow pixel values at the corner, which maybe the model will perceive it as that those pixel values are not very important, right? It gives a message to the model that those pixels are not very important for us, and we'll try to give more importance or more attention to the other pixels, which means that if you have an image, we'll try to tell the model, if I have an image like this one, without zero padding, I just tell the model that all informations except the informations around the perimeters are important. So the informations in the middle are more important compared to the informations which are given or which are located across the perimeter, right? So all informations across here are not very important for us because we will scan it only one time, and I mean the informations which are given inside the image is more important, has more importance compared to other pixel values, right? So which might be, I mean, negative message to my model that those informations around the perimeter, which we are getting from the perimeter or from those corner pixel values, are not very important for us, right? So in this case, we need to find a way to try to give more importance to the informations which are given at the perimeter by adding this zero padding. So add zero padding, we just add column and rows with zero values across the perimeter of the image. And in this case, when we do this scanning, when we apply this kernel, we will apply this kernel in that place. We will multiply those numbers because this is the weight value, in fact, 0, 1, 2, 3. It's pixel values or the weights. So this is omega 1, omega 2, omega 3, omega 4. Multiply those weight values with the pixel values and they take average, right? Or just a summation, whatever. So it will be 0 multiplied by 0. I need to clean it, in fact. So we can start from. Okay, I don't know why I cannot clean. Yes. Now we will apply this kernel value into that part. So it will be 0 multiplied by 0 plus 0 multiplied by 0. 0 plus 2 multiplied by 2, 0 multiplied by 3, so the result will be 0 here. We will add this 0 value here. We will move it by one pixel value. We will move it to that place. And we will repeat this process one more time. So finally, it will be 1 multiplied by 3. So we will get 3 here. 0 multiplied by 0, 1 multiplied by 0, 2 multiplied by 0, 3 multiplied by 1. So we will get this value here, 3. We will move it 1 by stride equal 1. So it will be 1 multiplied by 2. And 2 multiplied by 3, so it will be 2 multiplied by 3, it's 6 plus 2, so it will be 8, right? We will move it again, one step, 1 pixel, so we will go here, so it will be 2 multiplied by 2, it will be 4. we will go to the next line. We will start usually from left to right. We start from left to right, and the top to bottom, right? We will go down by 1 pixel, starting from that place here, right? I will make it by red. So we will apply our filter to that part. This is the, multiply those numbers again. So it will be 3 multiplied by 3, it will be 9. Move it by 1 pixel. So it will be 1 multiplied by 1 plus 3 multiplied by 2, which is 6. So it will be 7 plus 3 multiplied by 4, 12. So it's a 12 plus 7, which is 19, right? And so on. So in this case, we will apply this kernel into the input image, and then we will get this output. This output, we will call it feature map, right? We call it feature map. So we obtain this feature map by applying this filter to this image, by applying this kernel to this image. Each kernel, in fact, I want to represent it as a neuron. When it's 2 times 2, it will be like this one, a neuron with 4 inputs, right? So this one will be represented by a neuron which has 4 weights. So it's omega 1, omega 2, omega 3, omega 4. And remember, we have bias, correct? So in fact, each kernel can be represented by a neuron, and the size of the kernel will be represented by the number of weights which you have, correct? When it's 2 times 2, you will have 4 weights. When it's 3 times 3, it means you have 9 weights. It will be omega 1 until omega 9, plus bias, correct? And those weight values, we usually initialize those weight values by random values, and after that, we will apply those random values into each pixel. And in the training process, we will try to adjust those weights in a way to get some feature maps which make sense for us. So this is the whole idea. I mean, in image processing, usually there are some kernels which people use. So for example, if you want to get this edge detection, for example, if you want to get those horizontal edges or vertical edges, you need to select a kernel which will try to extract those features for you, right? But in image processing, there are very few kernels, in fact, which we can use. But in case of deep learning here, you can just select a number of kernels or number of filters, and each filter will be represented by a neuron, and the size of the filter will be represented by the number of weights here. So if it's 2 times 2, in this case, we have 4 weights. If it's 3 times 3, or 4 times 4, or 5 times 5, so it will generate number of weights proportional to the size of the kernel, right? And we will apply this kernel to this input image, and we will generate this feature map. So the idea here, we use this zero padding, because if we didn't use a zero padding, as you can see here, when we are using the zero padding, we will scan those pixel values across the perimeter several times, right? When we are using this zero padding. So look, if you can look into this this pixel value here as a corner, we will scan it 1 time here, and after that we will scan it 2 times when we move this kernel to the right, and then when we go back, when we go down 1 line, it will be scanned 1 time here, we will move it another time, it will be scanned another time here. So now we scanned it 4 times, right? Similar to other pixel values, all other pixels, which means that this pixel has importance similar to other pixel values. So in this case, when we add this zero padding, we'll try to give equal importance to the informations which are stored in those pixel values across the perimeter of the image. But if you didn't use zero padding as we did last time, we didn't scan it, we just scanned it only 1 time. So we used the number inside this pixel value only 1 time, and we scanned the neighborhood pixel maybe several times, which means the information, which means it will send a message to the model that the information which are stored in other pixels are more important than the information which are given by the pixels which are across the perimeter, right? And this is very important, because imagine that you are building a system for an autonomous vehicle, for example. So in an autonomous vehicle, I have an image, right? You have this image. And in this case, if we didn't use zero padding, I will not care a lot about the information which are coming at the edges, right? I will focus onto the center of the image, because this is the most important. I will focus in the information which are stored in the pixel values in the middle and in those places, for example, but not across the perimeter. And this is very dangerous in case of autonomous cars, for example, because maybe I need to detect if a person is crossing the road, for example. And when a person is crossing the road, this information will be stored in the pixel values across the perimeter, right? So if someone is crossing from the corner, for example, I will not pay too much attention to this information, and I will not use this information for making my decision if I need to drive or stop. Maybe I will just keep driving because I don't care. I give a message already to my model that I don't care that much about the information coming from the pixels around the perimeter, right? So maybe someone is crossing, he tried to cross, he has intention to cross. So in this case, he will just make decisions that, okay, keep driving and hit him and kill him, right? And it's because of the zero padding, for example, because my model will try to focus when you are driving. I mean, you need to watch, I mean, you need to be very careful. You need to be sure that, I mean, you have good view, for example, and you pay attention to people who are crossing a zebra cross, for example. But if you will not use zero padding, maybe this information will not be very, very important. And if someone is waiting at a zebra cross and he has intention to maybe cross the road, if you are human, maybe you will stop because you understand this. But if we didn't use zero padding here, maybe the information the model will understand is that the information coming from those corners and the perimeter of the image is not very important, and I will focus only on the information coming from the middle of the image. So maybe if you have a car driving in front of you, and if this car stopped suddenly, for example, you will brake. But if someone is crossing by a bike or coming, or an animal coming, crossing the road, for example, or someone tried to cross the zebra cross in front of you, and he still just started to move, for example, you will not pay too much attention to the information coming from those pixel values across the perimeter of the image. So zero padding is very, very important. So a pixel value describes how bright the pixel is and what color it should be. For example, in case of grayscale, close to zero means darker and vice versa. I mean, when it's zero value means it's dark. When it's white, when it's one, it's white. The stride by default, the filter stride is 1 pixel at a time. I mean, if you didn't specify it in your model, it will be by default, it will be 1 pixel at a time, for example. Sometimes either for computational efficiency or because we wish to downsample, we move our window more than 1 pixel at a time, skipping the intermediate locations. So because it will take more calculations. So as I told you, this is the kernel. So the kernel will be represented by 1 neuron. And when you apply it to one part, you will do some activation. So you will multiply those weights with the pixel values. You will calculate maybe the average, whatever, put it in this pixel value, for example. So if you want to do downsampling, because if we will move here each time by 1 stride, right? So we will do 1 activation. We will get the value here. We will move by 1 pixel. We will get another value here. So in this case, the output size will be 4 times 4, as you can see it here. If you use stride equal to, what will happen? If stride equal to, we will downsample the feature map, right? I will apply it here 1 time. I will calculate this value. After that, I will move it by 2. I will move it by 2 pixels, and I will do another activation, correct? Like this one. So if you want to downsample the feature map, you need to increase the stride, for example, but by default it's 1. By default it's 1. If you want to reduce the number of activations, because number of activations is number of calculations, right? So if you need to reduce number of calculations or number of activations, so if you want to reduce computational resources which you are using for training your model, in this case you need to increase the stride by, it should be used by 2 or 3, for example. So in this case, you will reduce number of activations, because number of activations, it's number of calculations. So if you want to train your model faster, for example, so in this case, you need to increase the stride by, should be 2 or 3, for example. So it's according to the kernel size. So the stride, it's by default, it's 1 pixel at a time. We will move this filter by 1 pixel at a time. Sometimes either for computational efficiency or because we wish to downsample, we move our window more than 1 pixel at a time, skipping those intermediate locations. So in this case, I will not have too much overlap between each activation, for example. So So if we need to revise one more time, the building blocks of those convolutional neural network, it's those layers, convolutional layers, pooling layers, and the fully connected layers. Now we are talking about the convolutional layers, and we are talking about the filters. So each filter is a neuron, correct? And they have both weights and bias, correct? Like normal neuron. And the input size is a fixed square, could be fixed square, for example, because usually it's a square, it's 3 times 3 or 4 times 4, 5 times 5. And we call it the receptive field of this filter, called a batch or a receptive field, right? So what about those pooling layers? When we apply those pooling layers, we try to downsample the previous layer feature map. So usually we apply this pooling layer to a feature map, not to the input. So if we can go back here, I mean, we apply this kernel to an input image. We apply this kernel here to an input image, correct? And we will get this feature map. Maybe this convolutional layer will be followed by a pooling layer. And the idea from having this pooling layer is to try to downsample the previous layer feature map. So, so the pooling layer follow a sequence of one or more convolutional layers and are intended to consolidate the features learned and expressed in the previous layer feature map, and they compress or generate feature representations and reduce the overfitting of the training data by the model. So this is the feature map. If we will apply 2 times 2 max pooling, for example, I mean, this max pooling, it's like also it does not have any parameters, right? It does not have any parameters. So it's just a downsampling approach. So if it's 2 times 2, for example, so we will apply it to this input feature map, for example. We will apply it to that part. So we will apply it to that part. If it's max pooling, for example, we will just select the max. What is the max between 0, 1, 3, and 4? It will be 4. We will move it by 1 when it's tried equal 1. So when we move it by 1, it will be applied to that part. Right? So what is the maximum from those 4 pixel values? It will be 5. Right? We will get this 5. We will go down and we will apply it to that part. We will get the maximum value between those 3, 4, 6, and 7. So it will be 7. We will move it by 1. When we move it by 1, what will be the maximum of this one? It will be 4, 5, 7, 8. So it will be 8. So in this case, we do some downsampling. So the input feature map, it was 3 times 3. And now the output feature map, it will be 2 times. So we do some consolidations or compressing, data compression. So you can say that it tries to compress this feature map into a lower dimensional feature map. We will reduce the dimension of the feature map. And it has two functions. In fact, the first, we try to consolidate those feature maps, and we try to downsample the feature map. This is very important because at the end, as we agreed last time, we will build a model, and the model will consist of convolution layers followed by classification part. And when we try to reduce this feature map for the classification for the fully connected layers, it will be easy to build a more simpler, less numbers of parameters in the fully connected layers when you have small small feature maps. So we will try to reduce the complexity of the classification part at the end, and it will help us to reduce the model complexity, number of parameters, so we can try to avoid overfitting. So it has 2 tasks. So the first one is to try to consolidate those learned feature maps. It will try to compress those feature maps, and also it has an important role also in so it compresses and generalize the feature representations and reduce the overfitting of the training data by the model. They have also a receptive field, and this receptive field, it's much smaller than the convolutional layer. The stride or number of inputs that the receptive field is moved for each activation is often equal to the size of the receptive field to avoid any overlap. So usually they move it by, it can be moved by 2, right? So you can move it by the size of the max pooling, for example. When it's 2 times 2, you can just move it by 2 each time. So we try to so it has a receptive field which is much smaller than the convolutional layer, and the stride or the number of inputs the receptive field is moved for each activation is often equal to the size of the receptive field to avoid any overlap. We try to avoid overlap here, right? So the pooling layers are often very simple, taking the average or maximum of the input value in order to create its own feature map. So usually there is max pooling and average pooling. Usually we use max pooling and average pooling. When it's max pooling, it's easy. We have, if the receptive field is 2 times 2, so we will, from those 4 pixel values, we will get the maximum. If it's average, we will just take the average, which is a summation of those pixel values divided by 4. So fully connected layers. So because we try to explain all different parts or the different building blocks of this convolutional layers of convnet, for example. So again, just to this is the input volume, right? And this input volume, we have some conv layers, right? We have those conv layers followed by max pooling. Usually we have this. We have some conv layers followed by max pooling. So this is the feature extraction part. This is the feature extraction part. And after that, we will have flattened layer. And this flattened layer, after this max pooling, we will have a feature map. We will flatten this feature map so we can put it in a one-dimensional vector. So this flattened layer, in fact, it will just convert those output feature maps into one output volume, and it's one-dimensional volume, one-dimensional vector. And after that, we will have those fully connected layers or the classification part. This is the classification layers. And this classification part, it can consist of number of fully connected layers. For example, we have one hidden layer, for example, this one hidden layer. And after that, it will be followed by an output layer, for example, right? So if we have a problem where we try to classify each example or each image into one of 5 classes, so in this case, we will use the softmax layer. And the softmax layer will have 5 outputs because we have 5 classes. And maybe the other hidden layer or fully connected layer, it will use ReLU activation function. And you need also to decide how many neurons in this layer, for example. And the input to this one will be the output from the flattened layer. And the output from the flattened layer, it will be the feature maps, but we will try to flatten it. We will try to put it into one-dimensional vector, right? So the idea here, when we use max pooling, we will try to reduce or downsample the original feature maps. And when we do this downsampling several times, we will try to reduce the number of input to the fully connected layers. And in this case, these fully connected layers, it will be simpler, it will be easy to train, and it will not overfit my problem. Because at the end, in fact, I mean, at the end, the most important for us is those fully connected layers, because this is the one which will make decision. This one will do classification. The conv layers, it will just try to extract features, right? It will not make anything. So in fact, I mean, before in shallow learning, we try to extract features by ourselves and try to feed it to the fully connected layers directly. But in case of conv nets here, or in CNN, for example, we will have those conv layers, and those conv layers, it will try to extract features, and it will feed it to the fully connected layers for classification. So the most important part for us is that part. In fact, this is a traditional part. But the feature extraction part, this is the new part, which will make life much easier for us, because the feature extraction layers, it will try to deal with the raw data, and it will try to extract those feature maps. And we will have those flattened layer between the conv layers and the classification part, because it will try to, the flattened layer, it will try to convert those feature maps into one vector of one-dimensional space. This one will be 1D vector, right? And after that, we will just transfer those inputs to the fully connected layers until we reach the softmax layers for classification. So the fully connected layers are normal, flat, feed-forward neural network. This is normal, as we did before. These layers may have nonlinear activation function or softmax activation function in order to output probabilities of class prediction. So maybe the output layer, it will be softmax, because this one, we needed to calculate the probabilities that each image belongs to each class, for example. But other layers, it can have different nonlinear activation functions. Fully connected layers are used at the end of the network after feature extraction. And the consolidations has been performed by convolutionals and pooling layers. We use this max pooling or average pooling because we need to consolidate those feature maps, and at the same time also we need to reduce the dimension of the feature maps to try to avoid any potential overfitting. They are used also to create the final nonlinear combination of features and for making predictions by the network. We will use those feature maps for classifying our problems. So the max pooling is very important because it will help us to consolidate those feature maps. And at the same time, also, it will try to reduce the dimension of the feature maps. So it will make life much easier for next conv layers. And at the end also, at the end here, we need to try to minimize the size of those feature maps as much as possible. So to make that part simpler, to avoid overfitting. We will use Keras for our building our conv nets, and the Keras provide an implementations of convolutional layers. We call it conv 2D, for example. So we will have a layer. I mean, we used the Keras before. We used those dense layers, but if we need to use CNN, we need to try to add those conv 2D layer, for example, and it requires the expected shape of the input image in terms of number of rows, number of columns, for example, its height, width, and number of channels. So we need to define this the input shape as we did before with dense layers, for example. So we need to define the input shape. And we need to define the filters, and the filter contains the weights that must be learned during the training of the layer. As I told you, each filter will be represented by one neuron. The filter weights represent the structure of the features that the filter will detect, and the strength of the activation indicates the degree to which the feature was detected, right? We will initialize those weights by random values, and after that, during the training process, the optimizer will try to increment those or adjust those weights in a way which can extract some meaningful features for our problem. The layers require that both numbers of filters be specified and the shape of the filters be specified. We need to define number of filters, and also we need to define the size of each filter. And stride, for example, if you didn't specify stride, it will be by default 1. Yeah. So the implementation in Keras, if you want to import a model, and model, we use the model also because we can build our model as a sequential using sequential API or model API, for example. So we need to import sequential and the model from Keras.models. From layers, we need to import dense because we will use dense for building our classification part. It's a dense layer, conv 2D, for example, and the max pooling. We need to have this conv 2D and the max pooling 2D, for example. When we build our model, it's just we need to import this sequential. We need to start with this, define our model as a sequential API, and after that, we need to add some dense layers of conv 2D layers, for example. For example, when it's dense layer, we need to define the input dimension, right? And we need to define maybe the activation function, which activation function we need to use, and also number of neurons in this dense layer. For softmax, if this is the hidden layer, we need to define an output layer or softmax layer. So the activation will be softmax. Maybe number of units will be 10. We don't need to define here the input dimension because the input dimensions will be imported automatically from the previous layer. So we need to define this one only for the first time. And after that, so this is how we build our model. We need to configure our model. We need to define the loss function. Maybe it's categorical cross entropy when it's binary classification problem, or when it's multi-class classification problem. We need to select the optimizer. We need to define the evaluation metric, for example. And after that, we will train our model. We will use X-train and Y-train for training our model. We need to define number of epochs. Maybe we need to define the batch size, for example, and so on. After that, we will evaluate our model evaluations. So model evaluation, for example, the loss and the metrics, for example, using this model.evaluate, and we will use X-test and Y-test for evaluating our model. And we can also try to use this model to deploy it using a predict. So for example, using X-test, for example, we can get classes or predictions. If you want to understand what is the meaning of those filters, for example, this is a very simple example for age detection, for example. If you want to do some age detection, so I have an image here. This is my input image, and I want to predict those vertical edges and horizontal edges. How can I get those from this image? How can I get those vertical edges and horizontal edges from this image, right? Because this is how we used to do it before. I mean, before having those deep learning stuff, we used to use those vertical edges. For example, we need to use a filter to try to get those vertical edges and horizontal edges from each image, for example. So how can we do this? So for vertical edges, for example, I mean, if you try to find any book, for example, for image processing, for example, book, you can find this vertical edge detection filter, this edge detection filter. So this is the filter, and we need to apply this filter to this is an image, and as you can see here, this image, it's 6 times 6 pixels. This is the image. 0 bytes, 0 pixel values means black, right? And non-zero means white. So this is the image. This is the input image. So I have here this vertical edge, which I need to detect. I have here a vertical edge, which I need to detect, for example. So I will apply this filter. I will apply this filter to this image. So we will apply it first to that part because it has this receptive field. Okay. It's crazy because I need to close this one. So we will apply it for the first time. We will apply it to that part, and we will calculate. It will be ones multiplied by tens, zeros multiplied by 10, 10, and 10 in this column. And after that, negatives multiplied by -1 multiplied by 10, plus -1 multiplied by this one. So when we apply this filter to that part, we will get 0 pixel value here. So it will be 0, which means it's dark, right? 0 means dark. We will move our filter by 1 pixel. We will apply those numbers again to those pixel values. So in this case, we will have 1 multiplied by 10 plus 0 multiplied by 10, -1 multiplied by zeros. So in this case, we will get 30, right? We will get 30 here. 30 means it's white pixel, correct? So we have a white pixel. We will move our filter by 1 pixel, and we will apply it again to this receptive field. So in this case, we will have ones multiplied by tens, zeros multiplied by zeros, negative multiplied by zeros. So the result will be 30. Correct? We will have 30. 30 also, it means white pixel. So it's white pixel. We will move it one more time. And we will apply this one to that part from the image. We will get 0, which is black. Correct? So the first row, in fact, in the output image, it will be 0, 30, 30, 0. 0 means it's black, white, white, black. Correct? So in this case, if you look into the original image, we have a vertical edge which we want to detect, correct? So when it's white, we will get 0. When it's black, we will get, when it's white, we got black. When it's black, we got black. But when it's the edge, it's aligned. This vertical edge, it's located between white pixel and black pixel. We need to detect that part. So when it's the distance or the area between white and the black pixel, which has an edge, we will represent it by white pixels. So in this case, we will be able to detect those vertical edge, for example. We will move back, right? We will move down by 1 pixel. We will repeat this process. We got 0, 30, 30, 0, and so on, right? So in this case, we are able to detect this vertical edge, right? So I have this, we have this vertical edge here, right? Applying this kernel into this image, we are able to predict or detect this edge. We have an edge here in that line, right? So, so higher pixel values represent the brighter portion of the image, and lower pixel values represent the darker portion of this image. Anyway, using this, imagine just compare this one. I mean, we have this filter, and this filter size is 3 times 3, for example. We have some pixel values here. This one, 1, 0, -1. I mean, in fact, those numbers, we obtained those numbers from mathematicians, in fact. So they just selected those numbers because we can convolve this filter with the image, and we can detect this edge using this filter. So those numbers has been decided by as mathematicians or maybe image processing expert, for example. He said that we can use those numbers because those numbers, by trial and error, we will be able to detect those vertical edge. For horizontal edge also, we can have another filter. So for vertical, so we can use this one for vertical, for example, right? So this one will be vertical filter for vertical edges to detect vertical edges. For horizontal, you can just rotate it, for example. When you rotate this one, we will get this one. So in this case, we can use this one for vertical edges. We can use this one for detecting those horizontal edges. Correct? Also, there are many different other filters. For example, this horizontally change and the vertically change, and the Sobel filter for spatial gradient, and so on. So in fact, when you open a book for image processing, you can try to find, you can get many filters for to detect each different types of edges, for example, right? And usually we need to apply different filters to the same image to try to get some features from this image, right? So those are the different types of filters. And in deep learning, in fact, or in convolutional neural network, I can decide, I can say that I need to have a filter of this size, 3 times 3. So I can say that I need to have a filter of 3 times 3, for example. So in this case, the filter size will be like this one, similar to this one, it will be like this. But instead of having those numbers in my filter, I will have some weights. So this filter will have some weights. It will be omega 1, omega 2, omega 3, omega 4, omega 5, omega 6, omega 7, omega 8, omega 9. And if I need to represent this one as a neuron, it will be like this one. I will have one neuron, and it will have those 9 weights, correct? Starting from omega 1, omega 2, omega 3 until omega 9, and the bias here. So in fact, I will apply this filter to one part from the image, and I will do some activations, and I will calculate a number here, right? And this number, it will be the pixel value of the new feature map. And we will repeat this process. I mean, when we build our model for the first time, we will initialize those weights with random values as we used to do. And after that, the optimizer will try to adjust those weights until we reach some numbers. And hopefully those numbers will be numbers which will make sense for us. So maybe if you want to, for example, if you want to detect those vertical edges, maybe it will end up with numbers similar to those numbers here, right? It could be. So we are starting from random values, and if detecting vertical edges is important for my problem, maybe the optimizer will try to reach those numbers by itself. Maybe if you have two filters, for example, I will apply vertical images. I need to detect the vertical edges, and in the second phase, I need also to detect those horizontal edges. So in this case, I will have two filters. One filter will evolve to this one, and another filter might be evolve also to this horizontal edges, for example. So it could be something like this. So just imagine that in image processing, in any image processing book, we have a small set of filters. But in case of deep learning, we can just imagine, you can just propose any number of filters in each convolutional layer, and the optimizer will try to adjust those weights in a way which will generate something which makes sense for our problem. Not only vertical edges or horizontal edges, but it might come with something crazy, for example, but it will make sense to our problem. Do you have any question for that part, please, before going to this bedding? Are you following me?
It's no question.
Okay, so what about bedding here? Bedding, it's convolving an input of 6 times 6 dimension with a 3 times 3 filter, for example. It will reduce the dimension of the image. I mean, the feature map, in fact, it will not be the same as the size of the input image. But if we didn't use bedding, the size will decrease. So if imagine that you have an input image of 6 times 6, and we'll try to convolve it with a filter of 3 times 3, for example. So in this case, the result will be 4 times 4. So if we didn't use zero padding, so the dimension of the output feature map, it will be less than that of the input image. So in this case, we can generalize it, and they say that if the input is n times m and the filter size is f times f, then the output size will be n minus f plus 1 multiplied by n minus f plus 1. So we can just have an example here. Yeah, so imagine that this is my image and it's 6 times 6, right? It will be like this one: 1, 2, 3, 4, 5, 6, for example. This is 1, 2, 3, 4, 5, 6. And if we need to apply this 3 times 3, so we will apply this one here one time. We will apply it one time, we will do one activation, so we will get 1 pixel value here. We will move it by 1. If the stride equal 1, we will move it to that part. We will apply it here. We will calculate the value of the second pixel, this one. We will move it one more time. So I mean the second time it was here, right? This is the second one. We will move it another time. So another step, another pixel value. So it will be here, right? We will calculate this value, correct? Again, we need to move it another, the last time it will need a different color. So it will be here, right? And we will calculate one value here. So in this case, in fact, if you repeat this process, so this is the input image, which is 6 times 6 pixel values. So this is the feature map. So the feature map will be 4 times 4, right? As you can see it here. So it will be 4 times 4. So the dimension will decrease, in fact. So if you don't use this zero padding, the dimension of the feature map will decrease. You need to be careful about this. But if you can use zero padding, for example, we can have an option that the output feature map will be at the same size of the input feature map or the input image, for example, right? If we use zero padding. When we use zero padding, we can add 1 row and 1 column around the perimeter with 0 values. It could be 1 or 2, for example. So in this case, we can try to keep the same size. We can try to do this convolution, and we try to keep the size of the feature map the same as the input feature map or the input image, for example. So there are 2 types of, there are primary 2 disadvantages here. Every time we apply this convolutional operation, the size of the image shrinks. So the size of the image will shrink. So pixels represented at the corner of the image are used only few numbers of times during the convolution as compared to the central pixels leading to information loss. This is very, very important. So we have two disadvantages if we didn't use this zero padding. The first one will be that the size of the input image will, the output image will decrease. We cannot call it input image, but it's a feature map. This one is feature map, right? So each time we apply this convolution, this will decrease, which is also good, in fact, because we try also to reduce the size of the feature map, because if we didn't do this, maybe the model will overfit, right? And therefore we use pooling, max pooling or average pooling. But this is not a very big problem, in fact. But the most important problem here is that we scan those pixel values across the perimeter very few times, compared to the other pixel values at the center point, center of the image, which gives a message to the model that the information coming from those pixel values are not very important compared to the information in the middle. And as I told you, this example, if you have this system in an autonomous car, maybe you will pay too much attention to cars in front of you compared to other information coming from the perimeters, from the corners and the sides. And the information coming from the sides are very, very important, because maybe someone is crossing a zebra cross, for example. So if you didn't pay attention, if your model will not pay attention to the information coming from those corners and the pixel values across the perimeter, maybe your car can do an accident, for example. So having those zero padding, it will help us to solve those two problems. So to overcome those issues, we can pad the image with an additional border. We add 1 pixel all around the edges. We can add this 1 pixel all around the edges. And this means that the input will be 8 times 8 matrix instead of 6 times 6. So if we can go back to the example, but it's not there anyway because I cleaned this image. So if you have an image which is 6 times 6, for example, right? If you will add this 0 around, if you add this 0 pixel around the edges, so it will be like this. So we will add this one here, right? So in this case, in fact, we added 1 pixel from here, 1 pixel from here, 1 pixel from here, 1 pixel from there. So in this case, the total size will be 8 times 8, correct? And instead of 6 times 6, it will be 8 times 8 because we added 1 pixel across each side, for example. So it will be 8 times 8 instead of 6 times x. And then when we apply this 3 times 3 filter on it, it will result in 6 times 6, not 4 times 4 as we did last time. But when you apply this filter here, when you apply 3 times 3 filter on this image, the output image or the output feature map will have the same size as the input image, which is 6 times 6, which means we can keep this original shape of the image. So there are 2 common choices for padding, one called valid and one called same, right? When it's valid, it means no padding. When you select padding equal valid, it means we don't have padding. So padding equals 0, b equals 0. So if we are using this valid padding, the output size will shrink. So it will be n minus f plus 1 multiplied by n minus f plus 1. And if you need to test this example, I mean when n equals 6, f equals 3, so it will be 6 minus 3, which is 2 plus 1, it will be 6 minus 3, it's 3 plus 1, it's 4. So the output size will be 4 times 4. So the size will shrink. When it's the same, here we apply the padding so that the output size is the same as the input size, right? When we select padding equals same, it means the output size will be the same as the input size. In this way, we don't lose lots of information and the image does not shrink either, right? So we will keep the same size. I mean, the output feature map will be the same as the input image or the input feature map. And at the same time, also, we will not lose too much information from the pixels which are located around the perimeter of the image. It will have equal importance to the other pixels inside the image, which is very important in some applications. Because the model will understand and the model will get the message, in fact. So even if you don't have intention, but the model will behave according to this way. So, okay. So stride, we talk about the stride or this stride convolution. So suppose that we choose a stride of 2, for example, while convoluting through the image, we will take 2 steps, both in the horizontal and the vertical directions. Usually we move in the horizontal and in the direction, and after that in the vertical direction by this stride size. So stride helps to reduce the size of the image. Stride of 2 or more reduces the overlaps and the correlations between the activations. So it will reduce number of calculations. So if stride number 1, you will do more activations. Of stride equal 2, you will reduce the overlap between each activations, and also you will reduce number of calculations because each activation it's 1 calculation, right? You can just I mean you can calculate it. For example, if you have an image which has 512 times 512 pixels, for example, and the filter size is 9 times 9, you can calculate how many activations of the stride equal 1 and if the stride equal 2. So it reduces overlaps and correlations between activations, and also it will reduce number of calculations or number of activations. This is an example of a stride of size 2, for example. So first we have this filter. We will apply this filter to this inception field, for example, and we calculated the output is 91. We will move it by 2. When we move it by 2, we will do another activations. We calculated this 100. We will move it by 2 again. So we calculated 83, for example. We will go down by 2 pixels because we will go first horizontal and vertical, correct? So we will move by 2 pixels in each direction. So we will go down. We will do these activations. We calculated 69. We move by 2, calculated 91. We will move by 2. We calculated 127. Go down by 2 pixels. Repeat this process. So finally, the output size will be 3 times 3, correct? So the input here was 7 times 7. And the output dimensions will be 3 times 3 when stride equal 2. So in fact, we did, how many calculations we did here? We did 9 calculations. When stride equal 2, we did 9 calculations. And also we reduced the size image or the feature map size. So the stride is very efficient. In fact, when we use, for example, stride equal 2 or stride equal 3, according to the filter size, we will reduce number of calculations, and also we will reduce the size of the output feature map. So if your model is, if the training process is very slow, for example, you can just increase stride by 1, for example, and you can see, the impact of the learning process. It should be faster. Yes. Convolution over filter over volume, because when we are working, we can, the input image, it could be like MNIST dataset, for example, which is 28 times 1, for example, because it's a grayscale image, but it could be RGB image, right? It could be RGB image. So here we have an example. The input size is 6 times 6 times 3, which is RGB image, which has a height of 6, width of 6, and the number of channels is 3, for example. When we apply a filter, in fact, we just decide the filter in 2D, right? We just decide the filter in 2D. For example, we select that the filter size will be 3 times 3, but when the input volume is 3D, the filter will be 3D as well, right? So suppose instead of 2D image, we have a 3D input image of size of shape 6 times 6 times 3. How we will apply the convolution on this image? We will use 3 times 3 times 3 filter instead of 3 times 3 filter. So it will be 3D filter instead of 2D filter. So the third dimension of the filter will equal to the third dimension of the input volume. So after convolution, the output shape is 4 times 4 matrix. So the first element of the output is the sum of the element-wise product of the 27 values from the input. So when you select this filter, so I can just explain it to you. So the output volume will be 1D. In fact, it will not be. So the feature map will be 1D. It will not be 3D. If you want to have a feature map of 3D, in this case, we need to select 3 filters, right? So I want to explain this one in more details. So this is the image, which is 3D. So this is RGB image, RGB image, red, green, and blue image. And you will select a filter size. Is in fact, in Keras also, you don't need to select it as a 3D filter, but it will be automatically understood from the context. So if I will apply this 3 times 3 times 3 filter, so this filter will consist of 29 weights. 3 times 3 times 3, it will be 27. Sorry, 27 weights, correct? So if I want to plot it as a neuron, so it will be like this one. Each filter will be represented by neuron. So I will have omega 1, omega 2 until omega 27. And remember the bias. And it will do this calculation, weighted sum, omega 1 multiplied as the pixel value. So I will apply this filter. So it will be applied to that part from the image, right? And also the green part here, I will draw it here. I need to select another color. So it will be applied to that part also here, right? And it will be applied to the blue part here. So those 27 weight values will be multiplied by those 27 pixel values, 9 from red, 9 from green, 9 from blue. And it will do this weighted sum, and it will apply this weighted sum to an activation function. And at the end, we will calculate a single value, and we will store this single value here. Correct? And after that, we will move by stride equal 1, for example, and we will repeat this multiplications one more time. This we will apply it again one more time. We will do one more activation, and we will calculate the pixel value here. So at the end, the size of the output feature map, it will be 4 times 4 because we didn't use zero padding, correct? We didn't use here zero padding, so it will be the size of the feature map will shrink, but also this one will be one-dimensional, correct? It will not be three-dimensional, it will be only one-dimensional. So each feature map will be one-dimensional because we apply only one filter, although the filter is the 3D filter. So we will apply this 3D filter to the 3D input, and we will calculate a single value. If you want to have different channels for this feature maps, you need to select a different number of filters. So if you select 3 filters, this one will be 3-dimensional. If you select 2 filters, it will be 2-dimensional, correct? Sorry, 2 channels. So because we have here one filter, it will be 1 channel. We will get 1 channel per each filter. So after that, we convolve over the entire, so 9 values for each channel. We will apply 9 values for each channel. So 9 values we will apply for red channel, 9 values will be applied to the green one, 9 values will be applied to the blue one. But at the end, we will take the summation of all those weights multiplied by all those pixel values, and we will apply this value. The weighted sum will be applied to some activation function here. It could be RALU, for example, and at the end, we will get a single value, single pixel value. We will store it here, and we will move by one, and we will repeat this process, moving by one stride, vertical and horizontal, until we scan the whole image. Please, if there's something not clear, please just inform me. So we will go to the next slide. So multiple filters, as I told you, when it's a single filter, you will get one feature map by each filter. But when you have multiple filters, we will get different channels for this feature map. So if I will apply this filter to this image, we will get one feature map. It will be 2-dimensional, 4 times 4. If you have another filter, you will get another 4 times 4 feature map, right? So this is very straightforward. So if we will have here 2 filters, in this case, we will have 2 neurons, right? So 1 neuron, 2, because they have 2 filters. So this one have weights from omega 1 until omega 27. This one also, it will have also weights. I will call it V1 until V27. We will do this weighted sum, apply activation function, weighted sum, activation function. So each filter map will generate one single value. So in the first activation, we will apply this filter for that part. We will get that part. We will apply this filter to the same part. We will get this pixel value. But of course, the weight values will be different, right? All those weight values will be randomized, will be initialized with different random values. So each pixel value, it should be different, something different, right? We don't know. Of course, it will be different in the first, at least in the first time, when we initialize those weights with different random values. So we will get different random values in those pixel values here. And after that, it will evolve until we get something which makes sense for our problem. So instead of using just a single filter, we can use multiple filters as well. So let's say that the first filter will detect vertical edges, and the second filter will detect horizontal edges, for example, from the image. Because maybe, I mean, before, for example, we used to build expert systems for images, for example, to say something about, to make some decisions or to classify the image. But at the time, we need to work with those image processing techniques using those vertical edges, filters for vertical edges, and to detect horizontal edges, for example. So in the same image, I can apply 2 filters, one to detect horizontal and one to detect vertical edges, for example. So it will be the same here. So the difference here is that each filter will be initialized with different random set. So each filter will detect different numbers, but the optimizer here in my model, it will try to evolve over, over time to detect something which makes sense for my problem. So if we use multiple filters, the output dimension will change. So instead of having 4 times 4 output, as it was in last example, for example, it will be 4 times 4 times 2, because we have 2 channels, right? So number of channels here will be connected with the number of filters. If you select 3 filters, this one will be 4 times 4 times 3, for example. And of course, when you increase the number of filters, you increase number of complexity. So the learning time will be longer, right? And maybe the accuracy will be much better because you have different filters and different feature maps. Okay. I don't know why today I have a problem. Okay, so one layer of convolution. We need to start with an example. We need to have an example. So once we got an output after convolution over the entire image, using one filter, we add a bias term to those outputs and finally apply an activation function to generate. I mentioned that already. So just remember that each filter will be represented by 1 neuron. So it will be like this one. It will be like this one. So it will be like 1 neuron here. If it's 3 times 3, so in this case, we will have 9 weights. So it will be omega 1, omega 2, omega 9. And we have here bias, weighted sum. And apply this one to the weighted sum to the activation function, right? It could be RELU, and get this output value. So this output value, in fact, it will be the output pixel value of the feature map. So we will apply this filter to We will apply this filter to the image, right? We will multiply those weights with the pixel values. We will calculate this weighted sum. We will apply the bias. Of course, it will be omega 1 multiplied by the pixel value plus omega 2 multiplied by the second pixel and so on, plus b at the end. So we calculated this weighted sum. We will apply this weighted sum to the activation function. It would be ReLU, and at the end we will have the pixel value as the output, right? In case of 6 times 6 times 3, when the image is 3D, so the filter size will be also 3D. It will be 3 times 3 times 3. So it's the same. So instead of having from omega 1 to omega 9, it will be from omega 1 to omega 27. So if you have 10 filters, for example, so each of shape 3 times 3 times 3, it's fine, right? It will be no problem at all. We will get 10. We will just get 10 channels for the feature map. So if the feature map will be 4 times 4 times 1, it will be 4 times 4 times 10, right? So no matter how big the image is, the parameters only depends on the filter size. So what is important here is the number of, it's the filter size, not the image, right? So in deep learning, in fact, we don't care about the size of the image. Of course, it will have some impact because it will take more activations, right? But it will not make any problem for us. So if your image is 256 times 256 or 512, the critical part here is that the time which it will take to scan the whole image, right? So the number of activations will increase, but it will be fine. Okay, so this is an example pooling layer. I mean, we'll talk about pooling layer already, but just again for last time, pooling layers are generally used to reduce the size of the inputs and hence speed up the computations, because we agreed that number of computations will depend on the size of the feature map or the input image, right? We can talk about the feature maps because we cannot apply pooling layer to an input image. So if the feature map has large size, number of activation will be very large. So we use this max pooling to reduce number of calculations by reducing or downsampling the size of the feature map. So we can speed up the calculations. And also it consolidate, in fact, try to consolidate those feature maps, right? And this is hyperparameter. I mean, it does not have any parameters, this pooling layer, but selecting the size of the pooling layer, for example, the filter in the pooling layer, and the stride, it's a hyperparameter, which you need to select. We need to have an example here. We will start with AlexNet, and AlexNet, it's a model which consists of 60 million parameters, and it uses ReLU as an activation function, right? We need to maybe play with this example and try to implement it. And as you can see here, this model consists of, I mean, those blue layers, it's the conv layers, right? So those are the conv layers, and each conv layer is followed by some max pooling layer. So this is conv1, CNN1, and it's followed by conv layer, by max pooling layer. And after that, this one, max pooling, we have this one, it's conv layer, CNN2, for example, and it's followed by max pooling, correct? And so on, right? So the input image is RGB image, which has a size of 227 times 227. When it's RGB, so we have 3 channels, one for each color channel, for example. And we will apply here a filter, this conv layer, it will apply a filter 11 times 11 with a stride equal 4, right? Do you see it? So this, the filter here, it's 11 times 11, not 11 times 11 times 3. Usually they don't care about the third channel. We just need to specify the height and the width of the filter, but we don't need to care about, we don't need to mention that it's 11 times 11 times 3. It will be understood by the context. So the filter size is 11 times 11, stride equal 4. How many filters here? We will get 96 filters. Can you see it? So imagine that it's only one filter. When we apply this filter to this image with a stride equal 4, the output feature map size will be 55 times 55 because we didn't use padding, we didn't use zero padding. So it will be 55 times 55 times 96 because here we selected 96 filters and each filter has a size of 11 times 11 in fact, times 3, correct? But we selected 96 feature maps. So this volume, in fact, this volume, it will be the feature map. It's 55 times 55. And how many channels? 96 channels. To this one, we will apply max pooling, 3 times 3 with a stride equal to. So it will down sample each feature map from 55 times 55 into 27 times 27. Right? And as you can see here, it does not have, I mean, it's a 3 times 3. So we'll apply this max pooling to each channel. So the number of channels will still be the same. So it will be 27 times 27 times 96. Because the max pooling, it's 2D. Max pooling, it's 2D filter, right? We don't have 3D max pooling, it's 2D. So we'll apply this max pooling filters to the feature map, which is 55 times 55. It will shrink it to 27 times 27. How many channels we have? We have 96. It's the same as this one, the original feature map. And after that, we will apply filters of size 5 times 5. How many of those filters? 256. So we'll apply 256 filters, and each filter has a size of 5 times 5. What will be the third dimension of this filter? Can you tell me, please? What do you expect? What will be the third dimension of this filter? First, we use the zero padding. It's the same. It's called the same. When it's the same, when apply zero padding equals same, in this case, padding equals same, it means the size, the height, and width of the feature map will be the same. It will be 27 times 27 as this one. So we didn't shrink because we used padding. We used here zero padding. But can you tell me, please, what will be the third dimension of this filter? We have this filter, it's 5 times 5, and we will apply this 5 times 5 to this input volume, correct? So the input volume has a size of 27 times 27 times 96. We will apply a filter here of 5 times 5. What will be the third dimension here, please? Are you following me? Is there anyone listening? Please, if you want to, if you don't want more, you can just tell me. We can just close it for today. Hello, guys. Can you hear me?
Could you please repeat the last calculation that you did, please?
Yes. So my question for this one, we have this feature map, and the size of this feature map is 27 times 27 times 96. And we will apply here a filter, and the filter size is 5 times 5. What is the third dimension of this filter? So do you know what is the size? What is the third dimension of this filter? This filter is 5 times 5. What will be the third dimension? So it's 96. So this one, it will be 5 times 5 times 96. And then when we apply this filter to this input volume, we will get a feature map of 227 times 27 times 1 channel. But how many filters from this type? We defined 256 filters. So when we do this 256 filters to this input volume, we will get from this size, from this feature map, we will get 256, right? We will have 256. So this volume will be 27 times 27 times 256. Is it clear? maybe we can just close today. Is it okay?
Yes.
Okay. So for the max pooling, next max pooling, we will apply this max pooling is 3 times 3 and the stride equal to. When we apply this one to this volume, it will shrink from 27 to times 27 into quarter, in fact. So it will be 13 times 13, right? But the same number of the channels will be the same, correct? Because this one, it's two-dimensional. We will apply this two-dimensional to each feature map one by one. So it will shrink the size into this one. We will do this down sampling. After that, we will apply a filter of size 3 times 3 and the zero padding equals same. So should expect that the output feature map will be the same as the input feature map. It will be 13 times 13. But here we defined 384 filters from this type. So we will get this volume. We will apply again max pooling 3 times 3, right? So no, it's not max pooling. It's just a filter of 3 times 3 times 384. With also maybe with same, because we got the same dimension here. So we will get this feature map. We will apply it one more time, but using 256 filters. So we got this size. And we will apply max pooling 3 times 3 with a stride equal to. It will shrink the size into quarter, in fact. So it will be 6 times 6. So we will go down from 13 times 13 into 6 times 6. It's a quarter because it will be like this one. This one, it's a 13 times 13. So the quarter, it will be 6 times 6 times 256. And after that, we will use flatten. We will flatten this one. We will have a flatten layer. And this flatten layer, it will convert this feature map into one-dimensional vector. The size of this vector will be the multiplication of 6 times 6 times 256, which will be 9,216. And after that, we will have fully connected layer of this number of neurons and another fully connected layer with this number of neurons. And at the end, we will classify, we will have a softmax layer, which can convert those input images into 1,000 classes, right? So this part will be the classification part. This part is a feature extraction part, right? So at the end, my model consists of those two parts. I mean, at the end, my model will consist of those two parts. The feature extraction part, which we apply to the input image. When we apply it to this input image, we will get this feature maps. We will flatten this feature map to get this one vector. We will apply this one vector to the first fully connected layer and to the second fully connected layer of this dimension, number of neurons. And at the end, the output layer will be a softmax layer, which has 1,000 neurons. And in this case, we will classify each input image into one of 1,000 classes of topics or objects, for example. So we have 1,000 classes. Maybe we can just stop here and we can start also next week, because I feel that people are getting tired today. I'm not getting any response. So and it's 12 already. So please let us finish here today, and we will start next time. We will revise those topics one more time next time, and they can start having some examples. Please just let me know if you have any questions, please. Any questions?
No questions on my side.
Okay, thank you very much.